Hey everybody, it's Wednesday, March 24th, and as you can see here in the aim today, our goal for today's video is to talk about how we can use concepts of angular momentum conservation to solve problems. Now, I don't actually ordinarily do this, but considering the fact that we are about where I usually am at this point in the year and the test is a little bit later this year, I think it probably is a smart idea for us to just take a beat and take one more day to talk a little bit about conservation of angular momentum problem solving before we move on to the next topic. And so, as you hopefully can tell from the worksheet that was attached to today's post, there is a worksheet with a series of 6 problems on it that I want to go through now. Again, I am going to ask throughout the course of this video that you pause at various points and think about the answers to the explanations and what the explanations would look like, and think about the solutions and try the solutions to the problems that I'm going to ask you to solve on this worksheet before you actually look at the answer, because the only way you're actually going to get this stuff down is if you try them on your own. Having said that, let's take a look at question number 1. Question number 1 on this sheet is an explanation. It says here, a rhinoceros beetle rides the rim of a horizontal disc rotating counterclockwise like a merry-go-round. If the beetle then walks along the rim in the direction of the rotation, will the magnitudes of the following quantities, each measured about the rotation axis, increase, decrease, or remain the same? The first part, part A, is asking, will the angular momentum of the beetle disk system increase, decrease, or remain the same, and why? Take a second to pause this video here and write down an explanation, come up with an answer, come up with an explanation. When you think you got one, hit play, and we'll go over it. So for 1A, it's asking you here about the angular momentum of the beetle disk system, and that's a crucial piece of information. The reason why it's a crucial piece of information, of course, is because the total angular momentum of the beetle disk system specifically remains the same. This is true because the beetle disk system exists in the absence of external torques. So that means the total angular momentum is conserved. The angular momentum before the beetle starts walking is equal to the angular momentum after it starts walking. And so the basic idea here is that because they ask you not just about the beetle and not just about the disc, but about the beetle and the disc together, the beetle disk system experiences no torque from any outside object, and thus the angular momentum is conserved. Take a second to pause this video here and write that down, adding any parts of this explanation that may be missing from your own. Of course, it's very important to remember, if you're talking about conservation of angular momentum, you have to mention the no external torques part, and when you hit play, we'll move on. Okay, let's move on to part B. Part B here is asking you about the angular momentum and angular velocity of the beetle. Will that increase, decrease, or remain the same? Since that question is really similar to part C, I think it would probably be a smart idea to just try both of these together. What's going to happen to the individual angular momenta and angular velocities of the beetle and the disk? Obviously, the key here, this is the only hint I'll give, obviously the key here is to really try your hardest to visualize the situation. What is actually happening to the beetle? What is actually happening to the disk? How is that going to inform you about their angular momentum and angular velocity? Take a second to pause this video here and try this problem, come up with an answer, come up with an explanation, and when you hit play, we'll go over it. All right, that brings us to 1B here. Let's talk about that one first. The angular momentum and the angular velocity of the beetle will increase. Think about it. The beetle had an angular velocity and thus an angular momentum, and it should be important to note here, the angular momentum is directly proportional to the angular velocity, so they're always in the same direction. The beetle had an angular velocity and an angular momentum due to the fact that it was sitting there on the rotating disk. It was rotating counterclockwise at the same angular velocity of the disk. However, if it walks in the direction of rotation, then essentially what it's doing is it's gaining more angular velocity and thus more angular momentum in the direction of its original angular momentum relative to the rotational axis. The key detail here, I think, is for you to really envision this as like a relative velocity problem, right? Like if a person is standing on a train and the train is moving to the right at 10 meters per second, the person is moving to the right at 10 meters per second. But if they start walking now relative to the surface of the train at 2 meters per second, then to somebody off to the outside, and in this case, the quote unquote somebody off to the outside is like the rotational axis, the Beetle has a relative velocity that is now larger. It adds, right? Just like the 10 and the 2 on the train would add to give you 12 for that outside observer. The new velocity relative to the disk plus the actual velocity of the disk results in an increased angular velocity and thus an increased angular momentum for the Beetle. We'll move on to 1C in a second, but take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now for 1C, the reason why I asked you to consider these together is because I really do think these answers are integrally related. The angular velocity and angular momentum of the disk have to decrease. The total stays the same, right? And so if the angular momentum of the Beetle goes up, the angular momentum of the disk has to go down to compensate. Here's the deal. In order for the Beetle to walk forward, it has to push on the disk in the opposite direction it's walking, so the reaction force can propel the Beetle forward. This force produces a torque that opposes the angular velocity of the disk, which causes the angular velocity, and thus the angular momentum, because the angular momentum is directly proportional to the angular velocity, to decrease. Since the Beetle and the disk are part of the same system, if the Beetle's angular momentum increases, the angular momentum of the disk must decrease in order for the total angular momentum of the system to remain the same. That's crucial. It's very important to realize in situations like this that the objects do exert torques on each other. That is how they experience changes in their angular velocities. The key detail is, though, about whether that torque is internal or external to the system. Notice when we considered both objects as part of the system, there's no external torque. But because the bug pushes on the disk, and obviously by Newton's third law, the disk pushes on the bug, each object individually receives a torque. Now, what I've usually found in years past is that kids find this kind of confusing. And I think the reason why kids find it kind of confusing, honestly, it just has to do with the fact that the thing is rotating. Don't go nuts. When we talked about conservation of momentum, it was not a shock to anybody that when objects smash into each other, they experience forces. They each experience a force. But the key detail is the net force on the whole system is zero. And the reason why the net force is zero on the whole system is because those Newton's third law action-reaction pairs cancel out when you're considering the whole system to be the thing the force is acting on. Take a second to pause this video here and write that down, adding any parts of this explanation that may be missing from your own. I know there wasn't a lot of space there on that worksheet. Maybe you want to put this in your notebook, though, because this point is very important and it does come up on AP questions quite a bit. And when you hit play, we'll move on to number 2. Number 2, it's a nice question. It says here, the rotational inertia of a collapsing spinning star drops to 1/3 of its initial value. What is the ratio of the new kinetic energy to the old kinetic energy? Now, it may seem odd to you that this is an explanation question, but I will say you may want to make sure when you're answering this question, even though it's an explanation, when you see something drops to 1/3 of its initial value, it should give you a pretty good idea about how to approach it. Take a second to pause this video here and try this problem out. Come up with an answer. Come up with an explanation. And when you hit play, we'll go over it. For number 2, the main thing that you need to recognize is you kind of have to do 2 things at once here for this problem. And the 2 things at once that you have to do is recognize that in order to be able to answer the question about the kinetic energy, you first have to consider what happens to its angular momentum. Now, luckily, based on all of the principles we've talked about so far, the answer to the question, what happens to the angular momentum, is nothing. It's conserved, right? And so what that tells us is the product of I and omega always has to be the same number. And so the idea here is quite simple. If the angular momentum always has to be the same number, and the rotational inertia becomes 1/3 of its initial value, meaning it went down by a factor of 3, then that tells us the angular velocity had to increase by a factor of 3. So in order for this to stay the same, if the rotational inertia decreases by a factor of 3, the angular velocity's got to increase by a factor of 3. And some of you might be thinking, well, cool. In exactly the same way that the angular momentum is based on I and omega, so is the rotational kinetic energy. It's based on I and omega. So don't those changes cancel each other out? One increases by a factor of 3, the other decreases by a factor of 3, so it's a wash? The answer is no. And the reason why the answer is no is because of the fact that the omega is squared. And so if you think about this in the style of a 1-1-1 rule problem, yes, it is true that the decrease in I would, by itself, make the kinetic energy decrease, but the fact that the velocity, or the angular velocity, I should say, the fact that the angular velocity increases by the same factor, but that factor has to be squared according to the equation, means that the overall kinetic energy is going to go up. 3 squared is 9. You have a 1/3 here, and 1/3 of 9, of course, is 3. So the kinetic energy increases by a factor of 3. Since there is no indication that there are any external torques on the star, the angular momentum of the star is conserved. This means that the product of the rotational inertia and the angular velocity must always remain the same. Since the angular momentum remains the same, if the rotational inertia decreases by a factor of 3, becoming 1/3 of its original value, then the angular velocity must increase by a factor of 3. It has to be the case in order for the angular momentum to be conserved, and it is just a law of physics that the angular momentum has to be conserved. The rotational kinetic energy, on the other hand, is directly proportional to the rotational inertia and directly proportional to the square of the angular velocity. The decrease of the rotational inertia by a factor of 3 would cause the rotational kinetic energy to decrease by a factor of 3, but the increase in the angular velocity by a factor of 3, since it's squared, would actually cause the rotational kinetic energy to increase by a factor of 9, if that was true on its own. And so that means the total rotational kinetic energy increases by a factor of 3. Take a second to pause this video here and write that down. I know it is lengthy. You did not get a lot of lines. This is a very important question. They love to ask this even on the AP test. I've seen it in the multiple choice before. And when you hit play, we'll move on to the calculations. All right, number 3, nice problem. It says a man stands on a platform that is rotating without friction with an angular speed of 7.5 radians per second. His arms are outstretched and he holds a brick in each hand. Weird. The rotational inertia of the man, bricks, and platform about the central vertical axis of the platform is 6.0 kilogram meters squared. If by moving the bricks, the man decreases the rotational inertia of the system to 2.0 kilogram meters squared, what is the new angular speed of the man, bricks, platform system? This, in my opinion, is about as straightforward as a conservation of angular momentum problem can possibly be. Take a minute to pause this video here and solve this problem, and when you hit play, we'll review the solution. So in this problem here, they tell us that the man is standing on the platform and they're rotating without friction with an angular velocity of 7.5 radians per second. That's our initial angular velocity. They, of course, also tell us that when the man is rotating with that angular velocity, the rotational inertia of the platform is 6.0 kilogram meters squared. We are also, of course, told that when the man moves the bricks, the rotational inertia decreases to 2 kilogram meters squared. And we, of course, are looking for our final angular velocity. So the main principle behind this problem is the initial angular momentum is equal to the final angular momentum. That is what conservation of angular momentum means in about as simple a way as you could possibly put it. And so if we expand that out a little bit, it means I naught times omega naught equals I final times omega final. And so if we're going to solve that for omega final, we get omega final is I naught omega naught over I final. And now we're ready to plug in our numbers here. We have our I naught, 6.0 kilogram meters squared. The omega naught, 7.5 radians per second. And then we divide that by the final rotational inertia, which is 2.0 kilogram meters squared. Now, what you should realize about these classic ice skater tricks is you already should have had a fairly good idea of what this number was going to work out as. Why am I saying that? Well, it's pretty simple. The first thing we should say is you should be able to tell just looking at the problem that the rotational inertia decreased. That means the angular velocity should increase. And what you should also be able to tell, especially based on everything we've said so far in this video here, whatever factor the rotational inertia decreases by, that's the exact same factor the angular velocity has to increase by. The fact that the rotational inertia here went from 6 to 2, or noticed decreased by a factor of 3, means the angular velocity is going to increase by a factor of 3. Pretty good. Omega final then is basically just going to be 7.5 times 3, and that comes out to 22.5 radians per second, or to 2 digits, 23 radians per second. Take a second to pause this video here and write that down, adding any parts of this solution that may be missing from your own. And when you hit play, we'll move on. Now let's step up the difficulty a little bit. This problem here says a horizontal vinyl record of mass 0.10 kilograms and radius 0.10 meters rotates freely about a vertical axis through its center with an angular velocity of 4.7 radians per second and a rotational inertia of 5.0 times 10 to the negative 4 kilogram meters squared. A piece of putty with a mass of 0.020 kilograms drops vertically on the record from above and sticks to the edge of the record. What is the angular velocity of the record immediately afterwards? Take a second to pause this video here and try to solve this problem on your own, keeping in mind that if this piece of putty is just going to be dropped on the vertical record on the edge, that it should give you a pretty good idea about how you should model it in terms of its rotational inertia. Take a stab at the solution. When you hit play, we'll go over it. So they tell you here that this record has a radius of 10 centimeters, or 0.10 meters. We are told that the initial angular velocity of this record is 4.7 radians per second, and it's positive. We are told that the record has a rotational inertia of 5.0 times 10 to the negative 4 kilogram meter squared. Now, some of you might be thinking, well, why are you writing that as I naught if that's the rotational inertia of just the record? It's important to realize the putty isn't spinning or revolving until it sticks to the record. And so it makes no contribution to the initial angular momentum of the system. The initial angular momentum of the system is due to just that of the record. The mass, we are told, of this piece of putty is 0.020 kilograms, and we're looking for omega final. As I mentioned in yesterday's video here, you're going to want to make very sure, in my view, that you solve these problems in a way that's going to make them as simple as possible without writing so much. In my view, the way to do that is to just move around all the symbols and solve for omega final first, and then make your substitutions. So what we're going to write here is I naught omega naught equals I final times omega final. And we're going to write here omega final is I naught omega naught over I final. Okay. Now we're ready to plug in. But first, we have to change around the equation a little bit. Now, the initial rotational inertia is just that of the record, so we're good. And the initial angular velocity is just that of the record, so we're good. But the final rotational inertia is going to get contributions from both the record and the putty. And it's very important to realize here that the putty should be treated as a point mass. It is not actually itself rotating, it is just moving around in a circle. And so we should treat its rotational inertia as mr squared. And now we are ready to plug this thing in. We have I naught 5.0 times 10 to the negative 4 kilogram meter squared times omega naught 4.7 radians per second. And then we're going to divide that by I naught 5.0 times 10 to the negative 4 kilogram meters squared plus, and then we have to do mr squared, which is going to be 0.020 kilograms times 0.10 meters, and then square it. And when you do all that math, making sure you're being careful about squaring the r in the bottom and adding those things together properly, when you do all of that, you end up with a final angular velocity of 3.36 radians per second, or to two significant digits here, we'll call it 3.4 radians per second. So yes, it does make sense here. We should first note that our angular velocity does decrease because a putty with a fairly considerable mass was dropped onto the end of the record, so it slows down. It has more rotational inertia now that there's a piece of putty stuck to it, and by it I mean the record, and so it slows down in order to preserve the same amount of angular momentum because there's no external torque. Take a second to pause this video here, adding any parts of this solution that may be missing from your own, and when you hit play, we'll move on. And that brings us to number 5. Number 5 here says, in the figure shown on the right, a 0.001 kilogram bullet is fired into a 0.50 kilogram block attached to the end of a 0.60 meter non-uniform rod of mass 0.50 kilograms. Oh dear God. The block rod bullet system then rotates in the plane of the figure about a fixed axis A. The rotational inertia of the rod block system about axis A is 0.120 kilogram meters squared. So they're giving us the rotational inertia of this whole thing right off the bat. That's the first important thing to realize. And it says here, if the angular speed of the system about point A is about 4.5 radians per second just after the bullet strikes the middle of the block, 0.65 meters from point A, then what is the bullet speed just before impact? It's important to realize here, they said this part is 60 centimeters. And so what they meant here is just that the bullet is going to strike here. Now, whether you realize it or not from the question, I think you should realize it, though, because it says here the angular speed of the system, and the system here is going to be the rod, the block, and the bullet. The point is the bullet sticks into the block. The question is, what is the bullet speed just before impact if the final angular velocity is 4.5 radians per second? Think about what the bullet is. Think about how it works in the context of this conservation of angular momentum problem. Pause this video here, give the solution a shot. When you hit play, we'll go over it. Okay, there's a lot of information that's actually given in this problem that you do not need. You do need the mass of the bullet. That is absolutely true, and I'm going to label it with the subscript B. The mass of the bullet is 0.001 kilograms, or 1 gram. They tell us here that the block is 0.5 kilogram. Don't care. They tell us that the rod is 0.6 meters long. Don't care. They tell us that the rod is 0.5 kilogram. Don't care. They tell us that the rotational inertia of that system, of the rod block system, is 0.120 kilogram meters squared. And that's why I don't care about the measurements of the rod and the block. Because we already know it's rotational inertia, we don't care about any of that. So once we have those two things, we have to recognize that obviously the final angular velocity here is going to be very important, 4.5 radians per second. And to be clear, because the bullet is not actually rotating, but will be moving around in a circular path once it sticks in the block, we have to model it as a point mass. And so the distance from the pivot point where it enters the block is an important measurement, 0.65 meters here we're going to label as R. We're looking for V naught, the speed of the bullet. And so, of course, we're going to start here with L naught equals L final. And so the thing I like about this problem, which obviously the AP likes about it too because they ask about it all the time, is that you have to realize for this problem, the angular momentum of the system before this collision happens is best given by the equation MRV. And that's because the only thing that has an angular momentum relative to that pivot point in the beginning is the bullet. And so we'll label this MBRV. And the angular momentum at the end, when the whole thing is swinging together, is really going to be best given by the equation I final times omega final. Now, your first move here, as I always say, it makes it a lot easier. Just solve for the thing you're trying to solve for. You solve for V, you get I final, omega final over mr. What you need to realize is that the final rotational inertia is going to be based on two things. It's going to be based on the rotational inertia of the rod and the bullet, but it's also going to be based on the, excuse me, I just said on the rod and the bullet. That's the rod and the block. It's also going to be based on the rotational inertia of the bullet. And because we're modeling that as a point mass, we're going to call it mr squared. Of course, we're going to want to multiply that by omega final. And then we're going to divide that by mr. And so now we're in business. We have here IRB is 0.120 kilogram meters squared. We're going to add that to mr squared. So we have the mass 0.001 kilograms times the r squared 0.65 meters squared. So that's our whole term here. Now we got to multiply that by omega final. That's 4.5 radians per second. And then we're going to divide that here by m times r, which is 0.001 kilograms times 0.65 meters. And when you do that math, making sure you have everything plugged in there very carefully, you end up with a final answer of 833.7 meters per second, which we can say is approximately equal to 830 meters per second. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own solution. And when you hit play, we'll move on to the last question. All right, and that brings us to the last question for today. This problem here says two disks are rotating about the same axis. Disk A has a moment of inertia of 3.4 kilogram meters squared and an angular velocity of positive 7.2 radians per second. Disk B is rotating with an angular velocity of negative 9.8 radians per second. The two disks are then linked together without the aid of any external torques, so that they rotate as a single unit with an angular velocity of negative 2.4 radians per second. The axis of rotation for this unit is the same as that of the separate disks. What is the moment of inertia of disk B? Take a second to pause this video here and try out this solution. This is a classic problem, and when you hit play, we'll go over it. So there's a lot of important information given in this problem, and since they labeled the disks already as A and B, we might as well label them as A and B as well. The rotational inertia of disk A, they tell us, is 3.4 kilogram meters squared. They tell us that this thing, disk A, so I'm going to call it omega naught A, is rotating with an angular velocity of positive 7.2 radians per second. They tell us here that omega naught B, the initial angular velocity of disk B, is negative 9.8 radians per second. We are then also told that after they are linked together, they move with a final angular velocity of negative 2.4 radians per second. And we are looking for the rotational inertia of disk B. So of course, like always, we start with conservation of angular momentum L naught equals L final. And now we have to think about what contributes to the initial angular momentum. Well, it's not actually that complicated. Both disks are spinning in the beginning. So we have IA, omega naught A, plus IB, omega naught B. And that's going to be equal to the two disks' rotational inertias joined together. Remember, they stick. This is like a perfectly inelastic collision times omega final. Now, what's a little bit annoying about this problem is you have to solve this for IB. And the way we usually write this means we got to distribute, gather, factor, but it's not that terrible. So we write here IA omega naught A plus IB omega naught B is equal to, and now we're going to distribute this omega final. So we have IA omega final plus IB omega final. And now we need to gather our like terms. I'm solving for IB, or the rotational inertia of object B, so I'm going to keep that on the left side. That means I'm going to keep this on the left side, so I have IB omega naught B, and then I'm going to subtract IB omega final. And on the right side, I'm keeping this here, so I have IA omega final, and then I'm going to subtract over IA omega naught A. I honestly don't think this problem is that hard. I think the most annoying thing about it is just all these damn symbols. But of course, you're just going to have to get used to that as we solve these. Now I got an IB in both terms over here and an IA in both terms on the right-hand side, so I can factor. I got IB equals omega naught B minus omega final. And then I have IA times omega final minus omega naught A. And that might look kind of weird because the order is reversed, but you should not think it is that weird if your rotational inertia for B comes out as positive because it's a scalar, so it should. So that means my final expression for IB is IA times omega final minus omega naught A divided by omega naught B minus omega final. And now we're ready to plug in. So I have here IA 3.4 kilogram meters squared times omega final, which is negative 2.4 radians per second, minus, and here's where you need to be careful because we have minus a positive number, so that one's fine, minus 7.2 radians per second. And then we're going to divide that by omega naught B, which is a negative number, negative 9.8 radians per second. And then, of course, we're going to subtract omega final, which means we are subtracting a negative, minus negative 2.4 radians per second. Of course, you all know how to do math, so this shouldn't be that crazy. And when you do that math, notice negative 2.4 minus 7.2 is going to be negative. Negative 9.8 minus negative 2.4 is still going to be negative. The negative divided by a negative gives you a positive. You do that math here, you make sure you plug it into your calculator correctly, and you get IB is equal to 4.41 kilogram meter squared. And we can say here that that's approximately equal to 4.4 kilogram meters squared. And I think that this is the perfect problem to summarize what I want to say about this topic of conservation of angular momentum, which is you will be considered a smart person if you draw parallels between this and conservation of momentum. Look at what happened. Each of these objects experienced an, if you will, angular impulse. And as we always said here, for linear momentum, the impulses are supposed to be equal and opposite. And so the key idea is, remember, just like we said, when objects collide, the object with more mass should experience a smaller delta V. Here, the object with more rotational inertia should experience a smaller delta V. And so notice, object A had to have its velocity go all the way from positive 7.2 to negative 2.4. That's a swing of about 9-ish, whatever. Let's just call it 9-ish. But object B had its velocity only change from negative 9.8 to negative 2.4. Changed by like 6, 7, whatever you want to call it. So the point is, you should be looking at those numbers and thinking before you even solve it, this one should be bigger than the other one because its velocity changed by less. Now that we've done the calculation and it is bigger than the other one, then we're in good shape and we know we solved the problem correctly. With that, that's it for today. Hopefully, this one final look at all of these conservation of angular momentum problems that you could solve sort of gives you a little more confidence with this stuff going forward. Obviously, as is always the case, please feel free to ask any questions you have about any of this stuff, and I'll see you tomorrow. Take care, everybody.